In this video, we're going to talk about linear correlation. What I mean is we want a way to measure whether or not data is in fact linear. Let me give you an example of what I mean. Consider these two scatter plots. To me, they both look linear, meaning I can envision a line approximating this data pretty well. In this particular set of data, I envision a positive line or an increasing line. In this data, I would envision kind of a decreasing or negative line or negative correlation. So we would say this is a positive linear correlation referring to the increasing nature of the data. And this would have a negative linear correlation referring to the decreasing nature of the data. It doesn't always have to look like that. Consider these two examples. This one doesn't even appear to have any relationship, linear or otherwise. The data is very scattered. It doesn't seem to relate to each other at all. Where in this one, it kind of looks like it has a pattern, just not linear. So for this, we'd say there's no correlation. This one, there's a nonlinear correlation. In other words, maybe another shape, like in this case, maybe some sort of exponential or logarithmic function might be better at approximating the data. But before you panic, we're not going to look at nonlinear. We're only going to look at linear. And here's what we're going to use. We're going to use the linear correlation coefficient to determine if the data is linear. It's going to help us measure the strength of the linear relationship and the direction of the linear relationship. Here's what I mean. This correlation coefficient, which is called R, was first developed by Karl Pearson. It's numerical, and it tells us how strong the linear relationship and its basic direction, meaning whether it's a positive or negative linear relationship. So here's how it's calculated. This horrible formula. I'm keeping it real. This formula you'd have to do for every single X and Y data value. And this is just awful. We will not be doing this by hand. We will use the calculator. Before I get to that, though, I want to tell you something about the linear correlation coefficient. It actually gives us some information. First of all, it's always between -1 and +1. If it's close to -1 or +1, that indicates that there's a stronger linear relationship. In other words, the closer it gets to -1 or +1, the stronger the linear relationship it exhibits. The further away from -1 and +1, the weaker the linear relationship. In fact, if it gets to 0, there's no linear relationship at all. So the closer it is to 0, the weaker or absolutely no linear relationship exists. If it happens to equal 1 or -1, then we have a perfect linear relationship, meaning they line up perfectly on a line. If it's +1, it's a positive correlation. If it's -1, it's a negative correlation. So the sign of R actually gives us information. A positive R means that as X increases, Y increases. We have a positive correlation. I showed you an example of that at the beginning. This is the example. As you can see, as the X values increase, the Y values increase, and it goes up in this positive pattern. A negative value of R means that when X increases, Y decreases, or a negative correlation like I showed you in this example. As the X's are increasing, the Y's are decreasing. So the sign of R actually corresponds to the slope of the line of best fit, which makes sense when you're kind of envisioning a line within the data. All right, let's talk about how to do this. So from our previous video, I had this data inputted in for L1 and L2. Go ahead and input that data into L1 and L2. And to find the linear correlation coefficient, we're going to do the same steps we did for finding the least squares regression line. It's stat, calc, and the number 8, linreg. However, we have to do something before we run this. We have to turn on the diagnostics. So if you do this once, it should be on forever unless your calculator battery runs out and you replace them. You'll have to do it again. But this is how you do it. You're going to go to second, 0, the number 0, and you see right above that means we're selecting catalog. And now we've jumped to the catalog. And in this case, the catalog is defaulted to alpha, meaning it's seeing all the green on our buttons. So I'm going to jump to D's by hitting X to the -1 because X to the -1 is associated with the D's. And then I'm going to arrow down until I see diagnostic on. Oh, there it is. Once I reach it, I'm going to hit enter. It's going to take me back to the home screen, but you must hit enter again and it will say done. Once it says done, you're good to go. The diagnostics are on. So now I'm going to go ahead and enter this data. As I said, if you haven't done that already, take a moment. Enter X is into L1, Y is into L2. And now I'm going to do the stat, calculate, and linreg. So stat, I'll write to calculate, and then number 8, linreg. It already defaults to L1 and L2, which I'm just going to go ahead and calculate. And now we'll see 2 new pieces of information. The bottom one, little r, that is our linear correlation. So little r, oh, sorry, I also wrote the least squares regression line. Little r is 0.66. What that means is, because it's pretty close to +1, we would say it has a positive linear correlation. I don't know if it's a super strong positive linear correlation, but it does have a positive linear correlation. Now, this other value, r squared, is actually another way for us to measure linear correlation. That is called the coefficient of determination. So r squared is the coefficient of determination, and it is literally the square of the correlation coefficient. So if you took little r and squared it, it's going to give you r squared. R squared is a percent. It represents the percent of variation in our y values that is explained by our x values. It's much easier if I explain this with our example. So we see that r squared is 0.4, I'll round it to the second place, so 0.44. What that means is 44%. So here's what that interprets. The least squares regression line is predicting the final exam score based on the third exam accurately about 44% of the time. I don't know if that's all that good. In other words, yeah, the third exam score does help us present the final, predict the final exam score, but it's not really all that accurate. If you flip a coin, that would have better accuracy than using the third exam score. So this is how accurate the least squares